So in this lecture, I'm going to now discuss hydroboration-oxidation of alkene nucleophiles. And this is a method of preparing an anti-Markovnikov, so that is the regioselectivity alcohol product. So there's two big things you need to know about this reaction. As I mentioned, it is anti-Markovnikov, meaning that the hydrogen is going to add to the more substituted carbon of the alkene. And it is stereospecific for a syn addition, because as we will see, this is a concerted reaction in which boron and hydride add across the double bond at the same time, and therefore syn, or from the same face. So THF is a solvent that does help to activate borane, but borane with a central boron atom lacks a lone pair, and therefore the boron is simply sp2, and it only has 3 bonds or 6 electrons around it, and therefore it has no octet. And what that means is boron is electron deficient, or an electrophile. And there's an empty p orbital that sits perpendicular to the sp2 plane. And that electrophilic atom is attacked by the nucleophilic alkene, where it adds to either face of this empty p orbital. So this is the first time where we've seen the fact that boron is the electrophile, or in other words, it's not the hydrogen, right? So in every other reaction in category A, we saw that the hydrogen of the strong acid was the electrophile. But now, when electron density starts to build up at boron as a function of being attacked by the nucleophile, the hydride actually attacks back at the alkene. And that is because this hydrogen is more electronegative than boron. And therefore, it's going to own more of the electron density in that bond and have nucleophilic character. So any alkene is polarized in this way, such that the less substituted carbon is better at stabilizing negative charge, and the more substituted carbon is better at stabilizing positive charge. And the boron adds to the less substituted carbon because it is actually the electrophile, or it's electron deficient at first, and then the negative charge resides at the hydride, or the nucleophile. So the electrophile was boron, okay, with its empty p orbital. And the nucleophile is first the alkene, but then the hydride. So this takes us to an intermediate that is charge minimized, where the pi bond is breaking. Boron is adding to the terminal position, and it keeps 2 hydrogens. It is breaking away from a hydridic hydrogen, which is forming a bond at the tertiary carbon. So you get this 4-membered ring transition state. And it is charge minimized, so the more substituted carbon that's better at stabilizing positive charge is diagonal to the electrophilic boron, and the less substituted carbon with more nucleophilic character is diagonal to the nucleophile hydride. And so because the hydride and boron add at the same time, they both add on the same face, or you get a syn addition, although this compound has no stereocenters in it. Okay, so it is anti-Markovnikov in that the hydrogen is at the more substituted carbon. But it's because in this reaction, the hydrogen was the nucleophile. That's all that changed. It's still true that the nucleophile adds to the more substituted position. This was the first time where we saw hydrogen as that nucleophile. So let me go through the second part of the reaction where we take that alkyl borane that we just made, and sometimes it will go on to alkylate many times. But for the purpose of this class, you can think of taking this syn addition product and then oxidizing it with hydrogen peroxide, which has this structure. So hydrogen peroxide has a very weak oxygen-oxygen bond, where these electronegative oxygens are not comfortable being bound to one another. And so this is great at donating an oxygen or doing an oxidation. And through a complex mechanism that we will not examine, there's a reaction where boron is replaced with the oxygen, effectively a hydroxyl group. The water is a solvent in that reaction, and the hydroxide is just a base. The actual oxidant is hydrogen peroxide. This is an oxidation because we increase the number of CO bonds. All I want you to know is that this reaction is stereoretentive. So whatever the stereochemistry of the carbon-boron bond was to start, it's the same in the product. And I'll show you that below. So if we're going to add an alcohol via hydroboration to this alkene, we have to think about, well, this carbon is tertiary, it's better at stabilizing positive charge. The secondary carbon is less substituted and better at stabilizing negative charge. So the nucleophile hydride will add to the tertiary carbon, the electrophile boron will add to the secondary carbon. So the alkene attacks the boron, and the hydride adds to the alkene. And that happens all in one step. So the boron, if it adds from the top, then hydride must also add from the top and push the methyl group down. Alternatively, if boron were to add from underneath, then the hydride would also add underneath, and the methyl will get pushed forward. So you get two stereoisomers. They are enantiomers. And you get syn products only, where H and BH2 are either both wedges or both dashes. So now after the oxidation, this is step one. After the oxidation, step two, BH2 is oxidized off and replaced with hydroxyl. And that is stereoretentive. So the wedged boron remains a wedge when it becomes the hydroxyl. Likewise, you get a stereoretentive reaction for the enantiomer. So in the end, we've taken this Z-alkene, cyclopentene, or methyl cyclopentene, and we've turned it into the SS and the RR enantiomers. It's stereospecific because we didn't get the RS or the SR enantiomer. We only got two specific pair of enantiomers from the specific diastereomer of starting material. So it is stereospecific for syn products only. So it is a syn stereospecific, but anti-Markovnikov describes the regiochemistry that the OH is on the secondary carbon. It's an excellent reaction for synthesis because we can control the stereochemistry and we can control the regiochemistry. We can control which carbons will be attached to the alcohol versus the hydrogen in the product. So similar thing here, I'll do it all in one drawing where we have a secondary carbon that is more nucleophilic and a tertiary carbon that's more electrophilic. and therefore OH and H can add from the back, which would push the methyl forward, or OH and H can add from the front, pushing the methyl back. Okay, and if you are to look at R and S, you'll see that this carbon has the R configuration throughout. That's a fixed chiral center that did not undergo reaction. The other carbon that undergoes reaction has configuration R in one stereoisomer and S in the other. So because one stereocenter stays the same while the other stereocenter changes, these are diastereomers. Specifically, the compound on the left is a chiral diastereomer, RR. But the compound on the right has a plane of symmetry down the middle. Let me show that a little better. Where you can cut straight through the hydrogen in the methyl group. There's a plane of symmetry. And so that is a meso compound. Therefore, it is achiral. Okay, so that's all I have to say about hydroboration. You can find practice with this reaction in Unit 2 of my Orgo 1 course guide at chemguides.com.